Hi everyone, and in this video I'd like to quickly go over a classic exercise in analysis, namely measure theory, and it states that any infinite sigma algebra on a set has cardinality at least that of the continuum. So I'll go over very quickly the relevant definitions here, and then delve into the proof of this statement. So let's recall, for x any set, we define a sigma algebra on X to be a set of subsets of that set X, that is, a subset of P of X, where P denotes the power set, such that sigma follows the following three axioms. The first is that the whole set X is in the sigma algebra. The second is that the sigma algebra is closed under taking complements, that is, if we have A in sigma, then X minus A, the set complement relative to X, is also in sigma. And the third axiom states that sigma is closed under countable unions. Now, an immediate consequence of 2, 3, and De Morgan's laws show that, in fact, if a sigma algebra is closed under complements and countable unions, it must be closed under countable intersections as well. So this is what it means to have a sigma algebra on a set. And now let's look at the other side of the inequality, where we have this little letter c denoting the cardinality of the continuum. So the continuum just refers to, in this case, the set of real numbers. So C is just the cardinality of the real numbers, that is, their size. Now a result of Cantor shows that the cardinality of the continuum is in fact equal to the cardinality of P of n. So the real numbers are actually put in bijection with the power set of natural numbers. The natural numbers are countable, that is, their cardinality is aleph null, the smallest kind of infinity. And from this, we have a result called Cantor's theorem, which is auxiliary, and it states that the power set of any set has strictly greater cardinality. This shows that if n is countable, the real numbers cannot be countable. That is, being in bijection with the power set of n, it must have cardinality 2 to the aleph null, so it is uncountable. Okay, how are we going to show the result that if sigma is any infinite sigma algebra on a set X, then the cardinality of sigma is greater than or equal to the cardinality of the continuum? Well, we're going to start with a certain lemma. And the lemma is going to be that under these circumstances, sigma always has an infinite sequence of disjoint sets. How are we going to prove this? Well, we're going to start with any arbitrary collection of countable sets. We're going to take E sub I to be such a collection, and this is going to be countable. We index it off by the natural numbers, and this is possible by the hypothesis that sigma is itself infinite. Now, from this arbitrary sequence of countable subsets, we're going to construct a new one, which then I will claim to be disjoint. We're going to take the starting set to just be the same, right? F sub 1 is going to equal E sub 1, and now from this, we're going to take this iterative definition where we now define the nth term in this new sequence of subsets f sub n to be equal to the complement of the union of all E sub I, where I runs from 1 to n minus 1, in E sub n. So the first three terms of the sequence are in blue on the right-hand side, where f2 is just the complement of E1 and E2, and f3 is the complement of the union of E1 and E2 in E3, and this continues. So I claim that this generates a sequence of disjoint sets, and for this we're going to assume, without loss of generality, that if we have two distinct indices n and m, we'd like to show they're disjoint, that n is less than m. Then the intersection of f sub m with the union of the E sub I as I runs from 1 to m minus 1 is empty. This is just by definition. This also shows, however, since one of these E sub I in the union is going to be E sub n because n is taken less than m. In particular, this result implies the weaker one, that f sub m intersects trivially with E sub n. And this goes to show, since f sub n is contained in E sub n, if fm and en are disjoint, fn and fm must also be disjoint when m is not equal to n. This proves the lemma that we have a disjoint sequence of infinitely many sets. Okay, now from this result, how are we going to prove the theorem? Well, we're going to consider a certain function constructed from the power set of natural numbers to the sigma algebra. It's going to take a subset of natural numbers and map it to the following union of f sub I taken above. The union is taken over all indices I that are in the set of natural numbers S on the left-hand side. An example of this is, let's say, if we take S to be consisting of the natural numbers 1, 2, and 4, then f takes S to the union f1, union f2, union f4. Alright, and we want to show now that this function f is injective because that means it is weakly increasing on cardinality. Since the f sub I are disjoint, we can consider the following. If f of s equals f of t, where s and t are two potentially different sets of natural numbers, that means that we have the following equality of unions, where the union across f sub I, where I ranges across s, and that across t, are going to be equal. However, since the f sub I are each disjoint pairwise, the only way for these two unions, the left and the right-hand side, to be equal are if s and t match exactly as sets of natural numbers. This implies that f is injective because if f of two potentially different values are equal, like f of s equals f of t, then s equals t, and the two arguments were equal to begin with. Now this shows that f is injective, namely the cardinality of the continuum C is less than or equal to the cardinality of sigma, and this is exactly what our result is, that the cardinality of sigma is greater than or equal to C. A corollary of this result that we have just shown is that there cannot exist any countable sigma algebra. This is of interest in its own right, and it shows that sigma algebras cannot be made too small as long as they are considered infinite. This is quite a strange and almost counterintuitive result, at least it was to me when I first learned this, that either they must be finite or totally tractable in some sense, or they must be uncountable to the point of having greater cardinality than the real numbers themselves. Thank you for watching this video, and I hope to see you in future ones.